class. Today we'll be talking about chi-squared test. Feel free to pay attention or not. Frankly, I don't care about your development as a student.
Dude, same.
Unfortunately, today our objectives include being able to: number 1, determine which chi-squared test is appropriate for the problem. Number 2, check conditions and assumptions. Number 3, establish hypotheses. Number 4, calculate expected values for each cell of the table. Number 5, calculate the chi-squared statistic. However, doing so requires knowing both the number of expected and the observed values. Number 6, assess the significance level with knowledge of the number of degrees of freedom. And number 7, finally decide whether to accept or reject the null hypothesis. Let's start by identifying all the chi-squared tests and when they each should be used. So let's practice, class. So our first test is a chi-squared test goodness of fit, which compares the distribution of one variable in one sample to a known or theoretical model population. Our second test is a chi-squared test of homogeneity, which compares the distribution of one variable in 2 or more samples representing different populations to see if they have the same distribution. Our third and thankfully our final test is a chi-squared test for independence, which compares the association between 2 variables in one sample to see if they're independent.
Let's try an example. A restaurant samples customers to determine if there is a relationship between customer age and satisfaction with the restaurant service. What kind of test is it?
Dude, I don't know. A 2 proportion Z test. Are you kidding me? Have you been paying attention at all? Why are you even taking this class? No. The answer is a chi-squared test for independence. We are sampling one group of people, the customers, and asking them 2 different questions: their age and their satisfaction with the restaurant service, to determine if they are independent of each other. Let's try again, Keith.
Okay, our next example. A consumer safety organization wants to see if there is a difference in seatbelt use in Los Angeles, California, Miami, Florida, and Dallas, Texas. Random surveys are taken in each city and respondents are asked whether they always, usually, sometimes, rarely, or never wear a seatbelt. What kind of test is it?
A chi-squared golf test? No! You are wrong once again! At least you managed to get the chi-squared part correct. However, the answer is a chi-squared test of homogeneity. We're determining if one variable, whether people, always, usually, or sometimes, rarely, or never, wear a seatbelt, has a different distribution in 2 or more samples. People in Los Angeles, California, Miami, Florida, Dallas, Texas. Let's move on.
And our last example. Do employees in traditional Monday through Friday office jobs tend to be absent on some days more than other days? Data on employee absences was collected from area businesses to investigate this question. What is the test?
It's a chi-squared golf test. Oh, you idiot! Oh, wait. You're right. We're comparing the distribution of one variable, whether employees tend to be absent on some days more than others. In one sample, the employees in particular businesses, to a known population distribution of employees who are absent. Good job, Keith.
Now let's try a problem. A public opinion poll surveyed a simple random sample of 1,000 voters. Respondents were classified by gender, male or female, and by voting preference, Republican, Democrat, or Independent. Results are shown in the contingency table below. Is there a gender gap? Do the men's voting preferences differ significantly from the women's preferences? Use a 0.5 significance level.
Now, Keaton, what is the appropriate test to use for this problem? Chi-squared test of independence. That's correct. Now, what is the first thing we should do when performing this test, or any other chi-squared test for that matter, Keaton? State the hypotheses. The first thing you must do is check the conditions and assumptions, that way your results are valid. Dude, my bad. So, Keaton, what are the conditions that must be met?
The conditions are, it must be a simple random sample. The data must be counts. And the expected values must be greater than or equal to 5.
Keaton, do you know how to go about determining if the last condition is met? No. Isn't it your job to tell me? So let's say I want to calculate the expected counts of males who voted the Republican Party. I would take the row total of 400 males Now to multiply that by the column total of 450 voted Republicans. So 400 times 450. Now take that completely and divide it by the sample size of 1,000, which then turns out to be 180. Repeat that steps to find every expected count, which I will fill in for us so it doesn't take up that much time. And as you see, our third condition has been met.
Conditions. Our null hypothesis is voting preference is independent of gender, and our alternative hypothesis is voting preference is dependent on gender.
Good. Now that we've calculated the expected counts, let's move on to performing the test.
So now let's move on to calculating our chi-squared test statistic. In order to do so, we must have our observed cells and our expected cells. To find the cell, we must take the observed minus the expected squared and divide that all by the expected, but take the sum of each cell. And that will turn out to be 16.2. Now that the chi-square test statistic has been calculated and you have shown the necessary work required, now let's move on to interpreting the p-value, which can be found using the calculator, utilizing a chi-squared two-way test. All you need is the chi-square test statistic and your degrees of freedom. Once calculated, the p-value turns out to be 0.0003, which is extremely small and is less than the significance level of 0.05. Therefore, we cannot accept the null hypothesis. Thus, we are able to conclude that there is a relationship between gender and voting preference.
Thank you for participating in today's lesson. I wish you the best of luck, I guess, with stats. Thanks for enough.